Okay, what's a rollup? Rollup is very simple thing. So at the end is we are maintaining a state. Mainly the state is a database of balances of people. We have a balance. This people has this amount. This people has this amount. Okay, and this database of balances, it's a current state, is a snapshot of a moment. Okay, we store that, and the idea is we Merkelize all that. We put that in a Merkle tree, so we get like a hash of all together. We have a root. Okay, and then what we do, what we're doing is we are forging batch. We are changing this state. So this batch is a set of transactions that actually what it does is modify these states. Very much like a normal blockchain works. But the here things is that the blocks, or what we call it the batch, just to distinguish between the blocks in layer 1 and the batches in layer 2, just to distinguish this. But we are creating these batches just as a normal Ethereum transaction. When we want to create a transaction, mainly what we do is we put a new state. Okay, this is the new state that actually forges a set of transactions. So this evolution from a state A to a state B with all these transactions, and we publish this new state in the Ethereum with a normal transaction. We call it this forging a batch. Okay, and the properties of zk-Rollup is mainly that besides the new state, we also give a proof that this state is valid, is correct. Okay, so it makes it a proof of a validity proof. We call it. It's at the end is a snark. It's a proof that's verified in the same smart contract, and it guarantees that this new state is correct. So that means that all the transactions that are included in these bytes are signed. That there is no double spending. That there is enough funds to send from one to the other. So that the state is correct. The state, it makes sense. Okay, so that's mainly what we are doing in our rollup. There is an important property that all the rollups needs to fulfill, and is that what we call it the data availability. If we are setting if somebody imagine an operator that puts a new state, but this state it's calculated from some hidden transactions from the operator, then the rollup would stop. Nobody would know exactly what's this new state. So in some way, we need a way to reproduce these states. So this is the data availability problem. We need to, in some way, in this smart contract, we need to prove that this data is available. In the case of our zk-Rollup, mainly what we do is just put all this data in the same transaction, in the same blockchain, but we put it in a very compressed way. We'll see this data structure. So this way, what we can do mainly is we can compress. This is the rollup effect. We can compress a lot of transactions in a single transactions. There are other options, validiums. Maybe they put it off chain or in a federated systems and so on. And there is optimistic rollups that they don't include this zk proof proving that, and they are more based on gaming. Somebody can challenge that this proof is not valid, and then they need to wait a little bit more in order to finalize. But zk-Rollups mainly what it works that way. Okay, so well, let's start going deep. And what's the state? What we have in this state? Well, this state is mainly, as I told you, it's a Merkle tree. In our case, it's a sparse Merkle tree. We could use a normal Merkle tree, but we choose a sparse Merkle tree because it has some cool properties for this. But here, what's in each leaf? What do we have in each leaf? Well, mainly what we have in each leaf is just a token. It's a token ID. It's an ID of which token are. Token 0 is going to be Ethereum. Token 1 we don't know. So people can register tokens in the mainnet, and this is every token will be assigned an ID. So we have a token ID. We have a nonce of this account. We have a baby jab public key here with the sign and the public key. You see here the third and the last one. This is a public key. We have an Ethereum address of this account. So we have this address that means that can be handled by an Ethereum address or by baby jab, here depending if we are in layer 1 or layer 2. And of course, we have the balance. It's okay. This account holds this balance. So that's mainly what we have. And in each leaf, we have one state. And this is a structure we are generating here. So mainly what we do is we get this structure. We put them, we hash them. We are using Poseidon in all the rollups. So this is the main hash function. We are putting the hash function, and then all these we merkleize all together. So this is what the internal structure of this very simple structure what we have. Okay. Well, just a brief introduction of what sparse Merkle tree. A sparse Merkle tree is a tree that it has, if you want, the as many levels as you want. We are limited here for the circuit just to 32 levels, but here sparse Merkle tree theoretically can grow as much as you want, and mainly it has two kind of blocks. This would be like a normal tree. When you have here is just the hash of the left of the right, and you go down to the tree until there is a point where there is only one key value. There is only one place. In this case, what we do is we hash different. We put a different hash, and then we just put the key value directly here. So we can have a structure that can grow. But just for the presentation, you can imagine that's just a normal Merkle tree, and it works the same way. Okay. So okay, and the other important structure, the other important data structure of the rollup is the transaction. What a layer 2 transactions looks like. Well, here is, you see here a lot of information, but let's go just one by one. So we have a signature constant. So because we are signing something that we cannot reuse these signatures here. Here is this probably a hash of this is a rollup transaction, and I have to move whatever. Okay, so this is a constant on it. There is a chain ID because Ethereum can hard fork. So here the transactions we already well we are just putting the chain ID here. The from index. So who is sending? Who is from? The leaf that's sending the funds. The to index. Okay, and the amount. Here you see that the amount is 16 bits. We'll see here that's very, if you want, we'll put the token. This would not be necessary because we already have in the index, the from index, we already know that on there. But we decided to put here just for security reasons, just for be sure that the user is signing to send this specific token and there is no confusion there. Anons, a user fee. You see here a user fee of 8 bits, and yeah, that's mainly it. Okay, there is the others. I will go the other here. Well, here is the destination can be a to index, but can also be an Ethereum address, or can also be a baby jab, and it can be even a combination of these. It must fulfill this and this. So we have these 3 things. Okay, and at the end, if you see at the end, here at the end, you see the signature. Okay, so the signature is baby jab. It's an EDDSA signature with Poseidon as the hash function. So we hash all these parameters together, and we put it all together. Here, let me go a little. Here is the 16, the float 16 that we are using here. You see it's a 5 mantissa of 10 bits. An exponent of 5 bits, and then 1/2 bit. It's like this is, you can see the formula here, but this allows to put any number with a precision of 3.5 numbers. 3 numbers, and the last number can be a 0 and a 5. This is the half bit here. So this is very natural way of talking about the money. If you see here, for example, this is a kind of so we cannot put any amount there, but we can set a lot of the normal amounts that a normal person would use on that. The other thing is the fee. The fee is just 8 bits, and here mainly it's a table. It's a lookup table of 8 bits, and we go from 0.00000. Well, from 0, the next one is 0.00001%. We go logarithmically. We have a lot of density in the what would be a normal fees, something between 0.001 and maybe 5%. So everything is in here, it's more compressed, and then we can go just 10%, 1,000%, 10,000%, and we can go high. So we have all the spectrum of all the possibles with more density in the what we understand that's the more normal ways, as a small percentage of a normal value for what you are sending. I want to tell that here in Hermez, the fee is paid with the same token that you are transferring. So if you are transferring Hermez tokens, for example, you will pay it with Hermez tokens. If you are transferring DICE, you will pay it with DICE. So every transaction goes to that. We will talk a little bit later about the fees. Okay. So and then here in the transaction, you see all these fields that start with RQ. This is for the atomic transactions. Most of them are going to be 0 here, but we will explain later on about the atomic when we talk about the atomic transactions. But mainly this is the conditions that the other transactions need to fulfill. That's why more or less all the fields are repeated here. Okay. So we have already what L2 transactions looks like. Okay, and what the circuit does. Well, the circuit mainly what it does, we start with a node, with a root, okay? We process a transaction, we get a new root, we process another transaction, we get a root, and we process 2,000 transactions, and then we have the last root, okay? So this is mainly what we are doing. Yes, there is a question or something?
Yeah, there's 2 questions, Jordi.
Go ahead.
Yeah, so the first is, how is Hermez network using DRAM-based random numbers? How is it better than the Starkware VDF and Chainlink VRF? That's first question, and then there's a second. I'll let you answer the first one first.
We well, for random numbers, you mean for the random beacon of the trusted setup?
You can check out if you read the chat.
Let me see.
Read the chat, and then yes, how it's scoped.
Yeah, moment chat. Right here, Igor. How is the Hermez using the rand-based? Random numbers. Yeah, well, this is we are using DRAM. We are not using Starkware because in the Starkware you don't have the code for generating the proof open source. So we decided to go to the DRAM, and well, it's just for the random beacon. It should be safe. It should be safe enough. We'll do exactly the same with the phase 2. We have the verification there, and that's what we have.
And then Igor has a question too.
Yeah, how data availability proofs are working at Hermez for Plonk-based rollups. zk-Rollup could be used to pass all data in the rollup. How solve this problem with gross 16-based rollup? Yeah, we'll explain. We'll go on that. We'll go on that later. I will answer you. I will answer Igor on that. If I don't answer during the presentation, ask me again. Okay. But you will see. Well, let me just move. Well, here what we do here is I started to do this. So we have these transactions. So mainly what we do is we need to verify that this from going from an old root to a new root, it's fine by these transactions. And well, one of the things that we need to do is also what we do is we get all this data availability. Here you see that this data availability is very short. It's the from index, the to index, which is 32 bits plus the mode, which is 16 bits, and the use fees. So we get all this data availability of all the fees, and we hash them all together. So in the circuit there is only one input. Actually, we'll see that in the circuit there is not only the hash of this, but the hash of all the other inputs, all the other parameters. So at the end, the circuit has a single public input, which is very cheap. And what we do is we do an SHA 256 of the data availability plus a lot of things. So I have another presentation for that. So we'll see later. Okay. So let's see a little bit more. Let's zoom in a little bit how the rollup circuits are organized. Well, we have the main rollup. Here I have when I will share the presentation. So here there is a link here. So here's a main rollup, which is the main project. So the main circuit done in Circum. Well, maybe you can push here. So I don't know if you can see it. So this is the main rollup. Okay. So here is all the inputs, and here you see the parameters. Here is the number of transactions. In this case, it's going to be 2,000. Number of levels is going to be 32. And then the max L1 transactions and max fee that we'll see later. Okay. So And this main rollup, mainly it's a placeholder for what? Well, we have the transaction. The transaction, we divide the transactions in two parts. Actually, it's a decode transaction. And then we have what's specifically a rollup, the rollup transaction, the transaction that we process. Okay, we have some, I will explain later on why we do that. Okay. Here, of course, with all these transactions, we hash them all together. So we have here a huge hash, SHA-256, as hash inputs that takes all the inputs, the data availability and many other things that we will see later. Okay, and then at the end, it's important to see a fee transaction. Mainly what we do for the transactions is we collect, so in each transaction, we sum up, we accumulate the transactions, and at the end, we get all the transactions of the different tokens. We have up to, in a block can be up to 64 different tokens. So, and then at the end, we just modify the state. So we change the root, we modify the state, we add these fees to the sum operator defined by the coordinator. So some account that it's owned by the coordinator, and this is added at the end of the rollup. Okay, so if we go a little bit more on that later. Okay, if we go in the here, if we zoom in again in a single transaction, what there is in the transaction, what we see in the transaction. Well, mainly what we see in the transaction are these two pieces, the processor 1 and processor 2. Actually, these two pieces, what it does, it modifies the state. So it goes to a leaf and it updates this leaf, maybe, or updates or inserts that leaf. We are processing. So this is, and why we have two? Well, because we need to, in the normal transactions, we need to update two leaves. The from, we probably need to subtract some value from the from, and the two. So we need to add into the two. So that's why we need two times. And this is, we are having these two processors that are the biggest part in when we're talking about constraints. Okay. What we do in the middle? Well, we have this state hash. So this is the state that we saw before. It's mainly is a Poseidon hash that gets a state and put it as the input of the processor. And it's gone. And we have here a balance of data. The balance of data, mainly what it does, it takes, well, it do all the math, it do all the calculus. It subtracts from one side, it adds from one side. It's also, when we do the deposit, it also do deposits, it calculates the fees, it sends the fees. So it do what would we do, what we can say the math of the transaction. Okay, and this is in this circuit. Okay, we have a fee accumulator, okay, that we will see later on. And two important things. We have a signature verifier. For layer 2, we need to verify that the signature is valid. So if the signature is not valid, then the proof will not be valid. So we need, in order to process this transaction, we need to have a valid signature. That's important. And of course, we have the request for the atomic transactions, the verification of the other one. We'll see a little bit more on that. Okay. Okay. With this, we have very much a transactions, so a rollup that works very good if we are only in layer 2. Okay. But what happened? How do I deposit to the layer 1? How do I deposit to the layer 2 from the layer 1? And how do I exit? So, well, let's start with the deposits. Okay. For the deposits, what we have here is a special kind of transactions that we call L1 transactions. So it's a L1 transaction is a transaction that somebody do in the smart contract. You do a smart, maybe a deposit in a smart contract, and then the operator needs to process these L1 transactions. We have different kind of transactions. This can be a deposit, can be a transfer, but let's think about the deposit, which is the typical L1 transactions. Well, what we do here is, well, we have mainly what we have is a queue of queues. Okay, so when somebody puts a transaction, we put it here in QE1. Okay. When somebody else put another deposit, it put it in the second slot of the QE1. Okay, and this queue is limited to 128 slots. If there is 129, then it's going to be put in the next one of the QE2, and so on. So people is adding transactions on that. Okay, and what from the smart contract, what we do is we force the operators to forge all these L1 transactions every 5 minutes. So when an operator forges these L1 transactions, then it can forge as many other batches as for during 5 minutes. But after 5 minutes, the next operator, the one that after 5 minutes, will be forced to forge the next QE. So we are, in some way, we are processing all the QEs. Every 5 minutes, we process one QE, and we force that by smart contract. So this way, there is no way that the balance, the deposit is going to stay in the middle, in the limbo of the smart contract. We know that everything is going to be deposited. Okay. Here we have the data structure. So mainly what we are doing here, we are constructing that in the same transactions, in the L1 transactions we are putting here. We have what we have in these transactions. We have the from Ether account. So when you are depositing, is the from of who's sending this deposit. The baby jab. Anybody can choose which baby jab. In this case, compressed. It's 156 bits. From index, you can do a deposit on top if it's a from index. But if from index is 0, then that means that you are creating an account actually. Okay. How much? This is set up by the smart contract. So when you are, so you need to, of course, you need to, if I'm depositing dice, of course, the smart contract needs to check in some way that you send the dice to the Rollup smart contract. Okay, the token ID and the token ID, and also in this transaction, in the same L1 transaction, we can do a transfer. So I can do a deposit on top of something and maybe sending this to somebody else, exactly in the same transaction. Why it's possible that? Because for a deposit, we're using just the first processor of the transactions, and then we can use the other one just for the destination. So in the first processor, we are adding the lot amount, we are subtracting the amount, and in the other one, we are adding the amount. This is very useful because this allows, for example, to do a single payment in the layer 1 transaction, but the second one receive automatically in the layer 2, and you are doing with the same transaction. You are doing one single deposit. Okay, so this is interesting because with this we can do layer 1 can do a transfer. For example, I can do a forced transfer. Okay, or I can do a forced exit. We will see it later. At the end is what we are doing is this. Okay. A cool thing of these L1 transactions, this would be like what we call it a user transaction. It's a transaction that the user do in layer 1. But there is another kind of layer 1. It's an operator just before, well, in the same transaction that's forging the batch, just before forging the batch, they can add L1 transactions there. Okay, and these L1 transactions mainly is for creating accounts. So an operator can create an account there. Okay, so this is very interesting because this allows, for example, to send from layer 1, send Ether or any token to a user that have no account yet, so have no leaf in the rollup. It doesn't exist in the rollup, but it exists in the account. Maybe have an Ethereum address or has a baby jab address already. So I'm able to send that. So I will process. I will generate this transaction. I will send to the coordinator, and the coordinator, what we'll do is, well, in the same transaction of forcing the batch, it will create the account, and after creating the account, we'll process the transaction. Of course, the transaction probably will have to have a little bit more of gas because the operator needs to pay for these other layer 1 transactions, but this can be very transparent for the user. Okay, and what we include in this layer 1 coordinator transaction? Well, we include a signature. Here, a signature mainly is a signature that's generated by the receiver, especially just to, in some ways, to link the Ethereum address and the baby jab address. It's a kind of I authorize this baby jab key for Hermez rollup creation. You are signing, so you are proving in some way that you have this Ethereum account. So this Ethereum account and this baby jab address, it's linked together. So this is created here. Of course, we put the baby jab. the token for this and the Ethereum address. So that's mainly what it does. It creates this account, but with this property. Then in the rollup, in the Hermez rollup, we are guaranteeing that the owner of the baby Jab Jab and the owner of the Ethereum address in the leaf is always is null or is the same. It's controlled. So that's why we are signing with one key to the other. Okay. Free processor. We explained it a little bit before, but here we go a little bit more in detail. Yeah, let's see, free accumulator step. So here what we do here. Well, let me just start here. So mainly what we are doing here, we are accumulating. We have in this case we have 64 accumulators, okay, and each transaction generates a fee to charge, okay, and it's added to one of those. It's added to one of those accumulators, okay, and this one goes. So and this goes accumulating, and at the end of the accumulator there is this fee transaction. But mainly what it does, it actualizes the root of there. So we are the fees, the coordinator get the fees in the layer 2. That's interesting because we're using the same layer 2 to collect the fees in here. Okay. Let's talk about the exits. Okay. How we have been, okay, we know how to transfer things in layer 2s. We know how to deposit things, but how can the users exit? Well, what we are doing here mainly is when a user is sending to the address 1, which is to the leaf 1, which is a special address, then that means it's an exit. And when we detect that's an exit, mainly what we are doing is we are maintaining another Merkle tree. So it's like another state. It has exactly the same format that the rollup state, but it's a state that in each block starts from 0, so it starts empty, and we are adding there all the deposits that are exiting. So here, what we do is in the processor 2, instead of modifying the old root state, what we are doing is modifying the exit root. So we are creating another tree that includes all the tokens, all the money that's exited in that block. So at the end, we have like at the end of the so after that all the transactions, we have a new exit route that includes all the exits that happen in that block. This exit tree is maintained in the smart contract, and then we can do a withdrawal. So mainly in the withdrawal, what we need to prove is that we have some key that belongs to this exit route, and so we have some tree that belongs to this exit route, and of course that we didn't have a kind of nullifier that we didn't withdraw it before. And all this we can do it. We can prove it with a normal Merkle proof, which is a little bit expensive to do it in Ethereum because Poseidon in Ethereum is expensive. But we can also use zero knowledge. We can also use a small circuit just to prove all this: the signature and the Merkle tree of the exit. And Hermez rollup allows both things. Maybe if with an exit that there is just a single exit in the batch, it's going to be cheaper to do it with just with a normal Merkle tree, maybe one level, 2. But if there is more levels, then you can go to the zero knowledge circuit. Okay, so here is how we do the exit tree construction. We start with an empty tree, and if it's an exit, then what we are doing is we are adding that into the exit. But it looks like it's the same. It's the same processor. We are recycling this processor because we are actualizing a tree that's has exactly the same format that the standard tree. And at the end we have the exit tree. Okay. Yeah, and this is what I mentioned you before. Okay, so all this, because when we're processing, for example, these layer 1 transactions, well, we are modifying the state. We are modifying here the layer 1 transactions. We are modifying the state. Okay, so we are creating new accounts and so on. So here, what we do is, well, we collect what would be all the public inputs, if you want, or public input outputs, and we are packing all them and doing just a single SHA 256. What we include in this public inputs outputs. We have we have here. Let's start with the third one: the old state root, the new state root, the new exit read. So we have these dates. We have all the layer one transaction full data. You know, all these. All these. Oh, sorry. So here, of course, the layer one transactions. Yeah, we have it in the smart contract, but we need to guarantee that this is current what we are processing in the input. So actually, what we do is we get we put all this input, we include in this hash. So it's like if we put all this everything that we have in the smart contract, and we put it in the circuit, and then in the circuit we check that everything is exactly what you have in the smart contract. So we are processing exactly these layer one transactions, and we have. So all these layer one, we have all these layer one transactions. We have all these layer one, layer two. This is what's data availability, the ones that we talked before. You know, these 4 fields, from, to, amount, and user fee. Here we have these 64. Well, this is the deposit address of where the fees goes on the operator. So what the mechanism is, the operator just sends in the transactions, put these fees. So these those fee indexes, we put it in the operator, and then we hash them together. So we see that actually these fees, so these fee indexes, so where the transaction fees goes is also valuable. It belongs to data availability. We know what needs to be included in the data availability in the call data of the forge block transaction. We have, of course, the chain ID here too, just to not for relaying attacks. Here we have also the current random batch. This is when we'll see that a little bit more later. And here we also have what's the old last, so the old last index and the new last index. So when we are inserting transactions, here the smart contract needs to keep control on what's the last index, the last leaf that's inserted. If you have 4 leaves, when you create 3 new accounts, then you will have 3 more leaves. So we need to keep control on that. So we need to be sure also that the indexes goes, the smart contract keeps coherent with the state. And we hash them all together, and we have this single public input. And this is the single input that goes to the public circuit. Okay. Yeah, I'm sure there is a lot of questions. I don't know if we are. Yeah, we're good in time.
Doing great on time, and I'll let you read it. Maybe I'll let you read the question right off the chat window. I just wanted to flag that there was a question.
Yeah, let me just read there because I have a poll here. Okay, yeah. Which one is the? I don't know. Igor, yeah. How many?
The latest. Yep. How many?
How many what?
Oh, sorry. Go a little below. The question is, how many transactions can be packed?
Yeah, okay. How many transactions can be packed in one block? And whether dynamic block size can be subparts. No, it's here we need to see, because we need to distinguish between what we call it a block and what we call it a batch. Okay, a block is for layer one. We reserve this word for layer one, and we talk about the batch. I understand that we are talking about the batch. In a batch, there is a fixed number of 2,000 transactions. There is one kind of transaction, it's a NOP transaction, so it should be less than 2,000. So 2,000 transactions at most. Okay, for layer one transactions. For layer one transactions, we accept only the user layer ones is 128. Okay, and operators layer one transactions are up to 256. So if you just use 2 users, you can do actually 254 operator transactions. So you can end up until 256 with layer one transactions, and the remaining transactions, or even less, so until 2,000, are just layer two transactions. Here, let me just go back a little bit. But here in the rollup transactions, here you see states. It's a rollup transaction states. Actually, is all this logic. Here is integrate all this logic. It's a layer 1. It's a layer 2. It's an exit. It's not an exit. So all these states or all these state variables are computed in this specific circuit here.
And then there's another question about, or just a clarification on hashing to a single public input, and is this a technique to save on gas fees or save gas fees on verification?
This definitely saves a lot of gas fees, okay, but it's also very convenient. Well, we already have we pack them all together, so it's also safe constraints inside the circuit. But yes, mainly it's for saving fees. Doing a hash in the Ethereum is very cheap, and then we just get a single input, and this input then it's in the prover is much cheaper if it has one single, it's just one field multiplication. It's just one group multiplication for the verifier. So that's much better. Okay.
That's I think that's all the questions that we have for now. So,
okay, let's move forward. Okay, so here we go a little deeper in one of the specific circuits. This is a fee accumulator step. So this is, for example, so well, if we started from here, okay, no, we started from here. Okay, so this is accumulator step. So now I'm zooming here the fee accumulator. How the fee accumulator would look like. So the fee accumulator will look like this. So this like there is 64 fee accumulator steps, okay? And each accumulator steps, mainly what it does is this. It's like, okay, you start from an accumulator. This is the input of the accumulator, and here in the multiplex we select if we select if we add it or not. So if it's not added, then the fee accumulator just copy it to the output. If it's added, just we select the one that's added. Okay. And what here we have an internal signal here that is already selected or not. If it was already selected, then we don't do anything else. Okay. So and when we select it here, when the fee plan matches the token, so this is okay. This is a right one. If this is a right one and it's not selected yet, then is when we added them. If not, then it goes. And it's like okay. So maybe it's like if is so it's just already was selected, the next one is going to be selected. So here is just an example of a very small circuit. Okay, that's a accumulator step. And then when we put all them together, we just put, and this is the fee accumulator of a single transaction. And when we go here and the fee accumulator, we accumulate all of them here. And at the end, we add the transaction fees. So this is, for example, how we add on this. Okay. Here's the last. Another example, just to have a detail of things how it works. The last index ID here is if it's new account, that mainly what we do is we increment. So we have this kind of circuitry for computing the new last ID. Okay. Yeah, one of the things that I announced in the main stage, and maybe I want to go a little bit deeper here, is the massive migrations. We are prepared for massive migrations, and how will it work? Well, mainly here we have this the hash that includes all the data availability. We have all these from and to. So how would it work? Let's see how it would work in Hermez, a massive migration. Okay, so imagine that there is a new version, it's Hermez 2, or there is a Uniswap layer 2 or something like that. There is another layer 2 thing. Let's think, for example, that's like Hermez 2. Okay, and we want people just to move from layer 1 is already decentralized, and we want people to move to layer 2 in a massive way. So here what we do is we will create this destination. In this case would be the Hermez tool. We call it the destination smart contract. Okay, but this DSC for abbreviation. This contract, what we do is we'll register a new account in the rollup. Maybe we do a deposit, or if you want a zero deposit, so we create a leaf there, okay? And then the people can start send tokens to that destination, to that index ID, to that destination leaf, okay? In operators, those send this to the destination index. The index means the destination index, so is the index of this rollup. Okay. Then we have, okay, in the rollup we already have funds received from many accounts in a single rollup account. So the smart contract can again do a force exit. A force exit is a layer 1 transaction that's sending, okay, just do a force. It's like force an exit. It's only from the layer 1. Of course, because the operator is forced to mine this, to forge these transactions, then the exit will be created, okay? And because it's created, then it can withdraw. So once exited, this smart contract can withdraw it. But the cool thing is that we can use the data availability hash to process all these transactions. We know all the transactions that this account received, and we can have this data availability hash to process those transactions in the layer. So in the layer 2 of the destination rollup. We have this hash, so we can process this new rollup. They will insert these addresses. We can use the state, and we can use the transaction hash. So we can use all the information, probably creating a circuit to process these massive migrations and update the state of the new rollup. But as you see in the layer 1, there is only one single withdrawal. There is one single transfer of the aggregated transactions until now of that token, of that contract. Okay, so this is a little bit how it works. So it's possible, and of course requires some work. It will require some work in the destination address, but this is actually possible there. Okay. I see some questions here. Let me read. Let me see. How many? I might have massive. I have missed your explanation, but is SSH 256 hashing all these into a single public input a technique to save gas? Oh yeah, we answered that. Yes. Okay. Contracts upgrade. Well, first of all, we want to disable that as soon as possible. That's the thing. But in the beginning, we have some security mechanism that it's going to be enabled at the beginning. We hope we can disable that very soon. And one of those is the contract upgrade. So in case that there is something wrong in the contract, we have this. The thing is that we cannot upgrade. So the upgrade has it's going to be 1 week delay for that. But as I told you, I hope that we can just fully decentralize. That means that this smart contract at some point will not be able to upgrade. Maybe we can use massive migrations to create another rollup, but it's going to be always an opt-out. It's not going to be forced on that. Okay.
There's a question in the chat, Jordi. Another about the previous slide. Yep.
So one additional circuit is used for DSC for bucket token. Batch token transfer. Yes, exactly. In the recipient, it will process an exit. When you do an exit, you will process, but you will have, because you have all the information there, you have the hashes of all this information. These hashes can be like the input of this new circuit, and then this circuit will process in the domain specific of the destination. Yeah, that's mainly how it will work. So one additional circuit is used for DSC for batch token transfer. Exactly. Yeah. The destination will have to have their own circuit to process all these massive migrations that comes from the rollup. But we have all this information, we have it packed and hashed, so it should not be difficult to process, to convert this this data that's already hashed there to the specific of these of the needs of this new rollup. We don't know how this rollup will be. Maybe using different corp, and maybe there is some conversion there. But definitely, it's possible to you have all the information in the smart contracts, and all this hashing can be inserted in this destination circuit. This is how it would work. I don't know if Starly it's answered that.
Did you see you saw the follow-up question, I think. So one circuit for DSC smart contract.
Yeah.
There's one circuit for batch load and one for smart contract.
Okay. Yeah, at least one, yeah. Maybe there is others, but yeah, at least one.
Cool.
Okay. So another thing, that's the safety mechanism. I don't want to go deep in here, but that's, well, the first again, this is a safety mechanism that we will start in the beginning, but we want to disable that very fast. This is it's a kind of escape hatch for just for the beginning. So how it will work? Well, first of all, if this is disabled, people just you have immediate withdrawal. When you withdraw, you just withdraw, and that's it. And this whole the system should work, and we hope we can enable this mode very soon. Okay, but what will be in the beginning? Well, at the beginning, it's going to be two kind of withdrawals. It's going to be a direct withdrawal and a delayed withdrawal. Direct withdrawal. The idea is that the direct withdrawal is going to be some rate limit. So it's not going to be possible to directly, maybe there is, I don't know, just 1 million tokens of each token per second. Actually, it's more complex than that. It's there is like 5 ranges of transactions, and there is a limit, for high value transactions, a limit for less value transactions, and so on. There is like 5 limits, and this can be controlled by a governance. Okay, but then if this system is, so if the rate is full, then the users can always do what we call it the delayed withdrawal. Delayed withdrawal just goes to another smart contract that's not going to be upgradable. We call it a withdraw delayer. And actually, this will, so you will be able to get the funds later on, maybe in just 1 hour, in 2 hours, in 1 day, or in some margin. In any case, this by a smart contract, this can never be more than 2 weeks. So this is the maximum delay that can happen. Okay. And during this delay, so the governance can switch. For example, if the idea is that, for example, if there is a problem and we detect some problem in the rollup, we can just put a very so we can stop direct withdrawals just by putting a very low limit. Okay, so we just stop withdrawals. So everything needs to go to the withdraw delay, and we can delay that to maximum 2 weeks. We can never get the funds, but we can delay on that. So here we can analyze things. Maybe we can update the smart contract, but see that if we can update the rollup smart contract, but we cannot update this. So everything that's in there, it's going to be there. And the only thing that we can do then is this withdraw the layer. We have a trigger. We have a trigger button, escape hatch button, that in case that we see that something that's mentioned, for example, a Poseidon break. Something breaks a Poseidon, or something really crazy happens on just a huge bug we found. Then what we'll do is we have an escape hatch, and then the funds and this withdraw the layer will go to some multi-sig with trusted members of the community, some white hats and people that's trusted, but it's not us. As I told you, we want to disable all these mechanisms. The idea is to direct withdraw for everybody, and that's it. And we hope we can reach this state of maturity very soon. But we'll see. And this is, we need to be comfortable. And this is just some safety mechanisms that we want to be sure that everything works in the right way, especially at the beginning. Okay. Another thing that we already talked, it's about the atomic transactions, how the atomic transactions work. Well, mainly what here is, and here is what we have, the decode transaction and the rollup transactions. The decode transactions, mainly what it does, it just gets part of the transactions, and it's so that imagine these centric transactions. You see this one that's black arrows goes here. Okay, so here what we send is we send the last 4 transactions and the next 3 transactions. Okay, the information of these transactions, and then we multiplex this to a single transaction, and this is a selector. So the operator can select which is the pair, the transaction that's related Okay, and the request verifier mainly is checking that what signed it, what we saw at the beginning, matches us with that transaction. This allows us to, for example, do an exchange. So I will send you this DAI, but with the condition that you send me this Ether behind, so that there is this other transaction that's mined in the other direction, and the other way around. So we have these 2 things. So we have these kind of linked transactions, and we can do these atomic transactions. Another thing that we added recently is a time limit. So we can, in the transactions, we have the time limit. If we go to the first slide, here, you see here all these request transactions are from, and here the other thing is the maximum batch. You see here, I don't know if you see my cursor some way, but that's, you see here the second block, and second is a maximum batch. And so this allows to create the transactions with a timeout. You know, it's like if this transaction is not forged by this batch, then this transaction is invalid. And that's the motivation why we are adding, putting as an input hashed, but as a public input the hash ID. Here is, so you see here, see the last thing that we hash is the current non-batch. Okay, so we have these things that I think we can be very convenient for exchanges or for payment channels, for different applications that can run on top of the rollup. Okay. Yeah, and the last detail is that it's a more technical thing, is that you see here. So instead of in the transactions, instead of computing the root in a serial way, here is we have a transaction, we compute the root, the transaction, we compute the root. This is very slow to process because there is this dependency, especially in Circom. So mainly what we do is we do a trick here. Is that what we do is, okay, so instead of calculating all these hashes in sequence, in order, actually is what we do is, okay, we just, as an input, we put all the inputs of all the transactions, so we can process these transactions in parallel, and then we add a single constraint that the output of these transactions is equal to this. Actually, we are not really solving the problem, we are just translating the problem outside the circuit, but outside the circuit, the things are much cheaper to compute, and we can do much faster. We can do it in parallel, we can use other techniques. And here in the circuit, we use it this way. So at the end, what we have is a parallel way of processing the transaction. So if you analyze the circuit, you will see that there is these intermediate signals. You will see, so it's just for optimization things. Okay, so this is my talk until here. This is a brief introduction of how Hermez network works, especially how the circuits work. We are looking for people to take a look at the reviewers. We would love if anybody is interested to review the code. Please let us know. We are probably going to create a group of people that wants to review that. As you can imagine, it's quite more or less, it's quite easy to find people that reviews, for example, smart contracts, but it's not easy to find people to review circuits because it's more new technology, and especially circuits in Circom and so on. So anybody that's interesting, it will be very helpful. There is some budget for that. So just anybody that wants to join, please contact us. We'll create our Discord account or something like that, but just join us, and that's the main goal. If somebody likes this and wants to know more about Circom, about Hermez, and that, please contact us. And yeah, that's my presentation. Let's go for more questions.
Great. So we actually have someone who's raised their hand up live. So I'll bring them up now. This is Garrett McDonald, and then we have another question from the chat. So let me actually see if this works here. Hopefully we can get Garrett in a second, and then take that question, and then I'll go to the chat.
Okay.
There's a little bit of a lag, just so you know, Jordi, between the chat and the actual.
Okay, let me see. Well, what's the last? Yeah, I'm getting lost here.
Yeah. Okay, maybe we'll just take Leo's question, and I'll DM Garrett, see if he meant to ask a question.
I'm going from the end. I'm going up. Can you talk a bit about performance? How long does it take to compute a proof of the circuit for 2,000 transactions? Oh yeah, a proof of the circuit right now, where we are just checking what's better in a CPU or GPU, but it takes about 2 minutes to compute this. It takes about 2 minutes to compute this proof, depending on how many transactions, if they are 0 or not. But the maximum, the limit that we are managing is about 2 minutes. Next one. Thanks a lot for explanation, Jordi. Yeah, you are welcome. Come on.
Yeah, I think you answered those. You answered those kind of in the course of the talk. So we'll ask here. So does anyone have any other questions for Jordi? And I just pinged Garrett to see if he wanted to ask his question live. Oh, there you go.
Where there is any tool to help transfer smart contracts to circuits. No, it doesn't work that way. So you need to build the circuits. Actually, we built zk-Rollup. You can go to zk-Rollup. Let me just write it down here. It's just, but go to GitHub, find zk-Rollup, is circuit compiler, which is very easy name. And with that, you can build. There are other languages, but this is the one that we are using here, and it's very easy. There is some tutorials, and there is also another, for example, there is another zk-Summit talk that I gave like 1 year ago talking about zk-Rollup. You can go through there, and it's very easy, but you need to create the circuits in there. And the Snark.js, which is this, let me just put here, Snark.js is it's a tool, and there are other tools, but the tool that in some way it converts this circuit in a, well, you need to do the trusted setup and all these, all the sequences, but at the end you end up with a validation key. And the validation key is what actually you have a smart contract where you can validate this proof. Okay, but in order to build circuits, you need to go to a specific language for building circuits. zk-Rollup is the one that we're using here, but there are others in the space. You can check each one. It has these different properties. zk-Rollup is like very straightforward. It's how it works. You know, it's just you just connect. It's very like for electronics. Eh? It's like a circuit. You need to connect blocks and just join things, and it's like a puzzle, and then you build the things. And this is how Hermez circuit is done.
Cool. And then there's we got, I think, so it's running out of time for the session, but we have 2 more questions. I think we can probably get to both. Leo in the chat has a follow-up question, and then we have another one just below that. So okay. Why don't we take those 2 and wrap it up?
Let me see, Leo. Thanks for the 2-minute number. How many constraints does your circuit have? 2 to the 27. So 128 millions. Yeah, can you talk a bit more about how long? Yeah, I think I'm done, right? I'm forgetting anything. I don't know if in the past I forget anything.
Sorry, there's one more question below. Will all circuit code be open sourced? And
it's already open source. It's already there. I see somebody already. Oh, it's Tony. Okay, Tony already put the. Oh no, it's not. Let me just go to the link. Well, you can see my screen here. So it's already open source. Here is the contracts. Here is the circuits. Let me just put and paste this in the. Oh, okay. Oh, okay. Yeah, Carlos. Okay, somebody already put there. This is the circuits, but here at Hermez Network, you can see here in Hermez Network, we will publish everything in here. Right now we have the contracts and the circuits, which is mainly the protocol, but here we will publish also the contract circuits. Have also here it's private already, but we will publish all these. We will publish here. We have the Hermez JS for the API, the Hermez node. We have the docs, contracts. This is private. You see, most of them are private, but we will release when we clean up and we put something that it's easy to read on that. Synchronizer, testing, compatibility. Well, here is a little bit internals, okay? But here is all the work that we are doing right now in the Hermez, and we will publish in the upcoming weeks. As I mentioned in main stage, the idea is to have a running test net for Christmas, more or less. And once we feel comfortable running this test net, then we will go mainnet. Hope this be very soon, but it's like we'll see how the things go. But what I can tell you is that we have the full team very committed to publish this as soon as possible, but at the same time as safe as possible. And we will not stop until we do it. So that's our commitment, and that's why we are working for. I think it's important having a roll-up of these properties with the scalability. Just having this real number of transactions with scaling all that and having this in the space and understanding how the roll-ups will work. This is very important for Ethereum in particular, but for the space in general. Roll-ups, I really believe that are the future for blockchain scalability, and this is the best thing that we know right now. So it's really an important step for the scaling space. Just together with I think we're out of time. So that's good. Just let me say that I'm very happy, for example, that Ethereum 2 right now, it's also it was funded, so it will launch like next week, the Ethereum 2, and this is very important also for the scalability, especially for the data availability in there. So the data availability together with the rollups, this actually is what I really believe that will bring this to mainstream. That's at the end is the goal. People use crypto everywhere.
Yeah, well, thank you that's a great call out, Jordi, because big accomplishment for the ETH ecosystem today. And thank you very much for your presentation. I think we all learned a lot, and I would encourage everybody in the session here to go check out our next session right after this. I think Leo from Algorand is going to be presenting a technique for aggregating vector commitments called point proofs. So I really encourage you to check that out after this, and I hope to see you around the rest of the event today. Thank you, Jordi. Thank you, everyone.
See you.